Our star, the Sun, is far from a quiet, unchanging ball of light in the sky. It is a dynamic, sometimes volatile, celestial body. On June 2, 2025, the Sun reminded us of its immense power. A significant solar event is unfolding. A massive solar storm is barreling towards Earth. Its leading edge will impact our planet in mere hours. This isn't just a minor solar hiccup, it's a substantial event. The trigger was a potent M8, two-solar flare. This flare erupted on June 1, 2025. Solar flares are immense explosions on the Sun's surface. The explosion launched a powerful coronal mass ejection, or CME, directly at Earth. A CME is a vast cloud of solar plasma and magnetic fields. When one is aimed at us, we pay very close attention. The journey of this CME across 93 million miles has been swift. Officials have issued a Level 3 or G3 geomagnetic storm warning. The next few hours and days will be critical. Stay tuned for updates. To truly grasp what's happening, let's break down the terminology. What exactly is a solar storm? It's a broad term. It encompasses several phenomena originating from the Sun that can impact Earth and our space environment. The primary drivers of significant space weather events are solar flares and coronal mass ejections, or CMEs. A solar flare is an intense burst of radiation. It arises from the sudden release of magnetic energy stored in the Sun's atmosphere. This energy is released as light across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. Solar flares are classified by their strength. The recent M8.2 flare is a medium-strong event capable of causing significant radio blackouts on the sunlit side of Earth almost immediately. However, the more substantial, prolonged impacts often come from CMEs. A coronal mass ejection is a massive eruption of solar material. We're talking about billions of tons of plasma superheated ionized gas and magnetic fields being hurled into space at incredible speeds. When a CME is aimed at Earth, it travels through the solar system like a giant magnetic cloud. If it scores a direct hit on our planet, it interacts with Earth's magnetic field, the magnetosphere. This interaction is what can trigger a geomagnetic storm. The current event involves both a significant flare and an earthbound CME, a classic recipe for a notable geomagnetic storm. Let's delve a little deeper into what happens when a coronal mass ejection, or CME, reaches Earth and triggers a geomagnetic storm. Earth possesses a global magnetic field, generated by the motion of molten iron in its outer core. This magnetic field extends thousands of miles into space, creating a region known as the magnetosphere. The magnetosphere acts as our planet's first line of defense against the constant stream of charged particles from the Sun, called the solar wind. When a CME arrives at Earth, it slams into the magnetosphere. The initial impact can cause a sudden compression of Earth's magnetic field. The orientation of the magnetic field within the CME is crucial. If the CME's magnetic field is directed southward, opposite to Earth's northward-pointing magnetic field, the two fields can connect. This process, called magnetic reconnection, allows vast amounts of energy and solar particles to pour into the magnetosphere. This complex interplay is what we monitor and try to forecast during these events. A G3 geomagnetic storm, like the one currently anticipated, is classified as a strong storm. While not the most extreme category, it can certainly cause noticeable and disruptive effects on our modern, technology-reliant society. One of the primary concerns is the impact on power grids. The geomagnetically induced currents, or GICs, can flow into high-voltage power transmission lines. These currents can overload transformers, potentially causing them to overheat and, in severe cases, suffer damage or even catastrophic failure. This can lead to voltage control problems, false alarms in system protection devices, and ultimately, regional blackouts. Communication systems are also at risk. Radio waves, especially high-frequency HF radio used for long-distance communication, can be severely disrupted. The ionosphere, which radio waves bounce off to travel long distances, becomes highly disturbed during a geomagnetic storm. This can lead to radio blackouts and a general degradation of signal quality. Satellite communications can also be affected. Geomagnetic storms can cause variations in the ionosphere that affect the propagation of GPS signals. Section 5. Decoding the G-scale. What a G3 geomagnetic storm means for us. To better understand the severity of these solar events, scientists use a scale called the G-scale. This scale, developed by NOAA's Space Weather Prediction Center, ranks geomagnetic storms from G1, which is minor, to G5, which is extreme. Each level corresponds to a certain intensity of geomagnetic activity and a set of potential impacts. A G3 storm, which is what we are currently bracing for, is considered a strong geomagnetic storm. At this level, power systems can experience voltage irregularities. Some protective devices on the grid might be triggered, leading to false alarms or even tripping systems offline. In some cases, controllable power fluctuations might occur, requiring grid operators to take corrective actions. While widespread catastrophic blackouts are more characteristic of G4 or G5 storms, a G3 event can certainly cause localized power disruptions. For aurora enthusiasts, a G3 storm is often good news, as it means the auroral oval expands significantly. The northern lights can become visible at much lower latitudes than usual. Section 6. Preparing for the celestial barrage, practical steps for safety. While the most significant impacts of a G3 solar storm are typically managed by infrastructure operators, there are still some practical steps individuals can take to prepare and mitigate potential inconveniences. Firstly, stay informed. Keep an eye on updates from official sources like NOAA's Space Weather Prediction Center. If you rely heavily on GPS for navigation, perhaps have a backup map or familiarize yourself with your route beforehand. Consider the possibility of power fluctuations or localized outages. If you have sensitive electronic equipment, you might consider unplugging it during the peak of the storm. Section 7. A silver lining. The breathtaking dance of the aurora. Amidst the concerns about technological disruptions, there's a truly magical silver lining to a strong solar storm: the enhanced visibility of the aurora. The northern lights, or aurora borealis, and southern lights, or aurora australis, are natural light displays in the sky, usually observed in the high-latitude regions. They are produced when the energetic, charged particles from the sun, funneled by Earth's magnetic field, collide with atoms in the upper atmosphere. These collisions excite the atmospheric gases, causing them to emit light of various colors, painting vibrant dancing curtains across the night sky. During a G3 geomagnetic storm, the auroral oval expands significantly equatorward. This means that people living at much lower latitudes than usual have a chance to witness this spectacular phenomenon. For the current storm, stunning northern lights are expected to be visible on Monday, June 2nd and Tuesday, June 3rd, across a wide swath of the northern United States. The colors of the aurora depend on which gases are being excited and at what altitude. The most common color is a brilliant green, produced by oxygen atoms at altitudes of around 60 to 150 miles. Witnessing this celestial ballet is an unforgettable experience. Section 8. Chasing the lights. Tips for an unforgettable aurora viewing experience. If you're hoping to witness the auroras during this G3 storm, a little preparation can greatly enhance your chances of a successful and memorable viewing. First and foremost, timing is crucial. The best viewing window is typically between 10 p.m. and 2 a.m. local time. This is when the sky is darkest and auroral activity often peaks. Location is key. Find a spot with a clear, dark sky, ideally away from city lights. Light pollution from urban areas can significantly wash out the fainter auroras. Give your eyes at least 15 to 20 minutes to fully adapt to the darkness. Don't forget to check the weather forecast for clear skies. Clouds are the aurora chaser's nemesis. Your smartphone camera might be more sensitive to auroral light than your naked eye. Try taking a long exposure photograph. Dress warmly. Even on a summer night, standing outside for extended periods can get chilly. Section 9. The dual face of solar activity. Preparedness in an electrified universe. This ongoing G3 geomagnetic storm, with its potential for disruptions and its promise of beautiful auroras, perfectly encapsulates the dual nature of solar activity. Our sun is the lifeblood of our solar system, providing the light and warmth necessary for life on Earth. Yet it is also a powerful and sometimes tempestuous star, capable of unleashing colossal amounts of energy that can significantly impact our technologically advanced civilization. We live in an electrified universe, and our star is its primary engine. The challenges posed by solar storms highlight our increasing reliance, and therefore vulnerability, on sophisticated technologies. Events like the current G3 storm serve as important reminders, and in a way, as drills for potentially more severe events. Scientists warn that humanity is not yet fully prepared for an extreme G5 solar superstorm. This underscores the critical importance of continued research, improved forecasting capabilities, and enhanced infrastructure resilience. By understanding the science, investing in preparedness, and fostering international cooperation, we can better navigate